Good morning and welcome back to Modern Physics Session 7. So today we will continue with vector atom model. That is, we have to extend our understanding on vector atom model to explain spectra, or say how is it possible to explain the observed spectra of various elements. So we have to use vector atom model to account for this. So spectrum is nothing but a collection of light or energy emitted by the atom. According to Bohr atom model, electrons revolve around the nucleus in a specified orbit, and each orbit is having fixed energy. And there is that when electrons jump from higher energy orbit to inner orbit or low energy orbit, the difference in energy is emitted, which constitutes spectrum. But it could not explain even the multiple lines observed in H alpha line. That is, Balmer series is having H alpha, H beta, when that H alpha is having different components, which could not be explained. So then complex spectra of many electron systems, then Zeeman effect, Stark effect, etc. So in all these, Bohr atom model failed. So in order to account for all these, we use quantum numbers and quantum vectors as predicted by quantum based atom model. Say an atom model with mathematical approach, and that is what we call vector atom model. Okay. So according to Bohr atom model, energy of the electron in an atom is determined by the principal quantum number n. That is, energy is inversely proportional to n square. We have seen that expression. But vector atom model says that the orbital angular momentum of the electron is decided by the orbital angular momentum quantum number L, and the component of orbital angular momentum in a specified direction is determined by magnetic quantum number ml. Right? So in the last session, I had mentioned that energy of a hydrogen atom does not depend on the orbital angular momentum L or magnetic orbital angular momentum ml. Or to say, each energy level En will be having more than one distinct state having same energy but different quantum numbers, and that is what we call it degeneracy, which is as peculiarity what we see in vector atom model. Or in Bohr atom model, there is nothing like degeneracy. And this idea of degeneracy could successfully explain many of the behaviors exhibited by the atom, particularly the complex atomic spectra and various phenomena like the Zeeman effect, Stark effect, etc. So today we will try to analyze how to explain these various additional lines observed in complex atomic spectra using this vector atom model. We had seen in our earlier discussion that vector atom model rests on spatial quantization and spinning electron hypothesis, which in turn are centered around two fundamental ideas called quantum numbers and quantized vectors. So each electron in an atom is specified in terms of quantum numbers n, l, ml and ms, four quantum numbers. Mathematically, their behaviors can be visualized in terms of quantized vectors like orbital angular momentum L, spin angular momentum S, and the total angular momentum J. Now we will see the kind of mixing of these angular momenta of various electrons in an atom to represent the atom as a whole. Or say we will explore there is various kinds of coupling or some kind of interaction between these component vectors of various electrons in an atom that will describe various behavior exhibited by the atom. So we have to explain atom as a whole, not as electrons. So this coupling will introduce various spectral notations and various energy levels which can account for the observed spectra or spectral response in electric or magnetic field, etc. We had seen spectroscopic notations like L, S, J, SP, D, F, G, etc. for electrons. So while considering or talking about atom, that is when electrons are considered together or various vectors are coupled to represent atom as a whole, these identical, more or less identical notations are used. For example, for atom we use capital letters like capital L, capital S, capital J, then capital S, P, D, F, G, etc. That will describe this atom as a whole. So in an atom having two or more electrons, the orbital and spin angular moment of all its electrons can be added together in two ways. And accordingly, there are two types of coupling schemes. The method of combination, which depends on interaction or coupling between the orbital and spin angular momenta. And these two types of coupling, one is LS coupling or Russell-Saunders coupling, and the other is called JJ coupling. So we will analyze them there is LS coupling we will see in detail, but JJ coupling we will not go for much. We will just peripheral we will see and proceed. So here LS coupling or Russell-Saunders coupling. So this occurs most frequently and hence it is known as normal coupling. So in this coupling, all the orbital angular momentum vectors of the different electrons combine to form the resultant orbital angular momentum capital L of the atom. Similarly, their resultant spin or various spin vectors of electrons, they will be combined and it will give the resultant spin capital S of the atom. And then this capital L and capital S combine to give the total angular momentum J of the atom. That will describe the atom. So symbolically you can write capital L, vector L is equal to the vectorial addition L1 plus L2 plus L3, and the capital S is equal to vectorial addition S1 plus S2 plus S3, etc. And the corresponding orbital, this total angular momentum J is vector sum of L and S. But actually it is a more involved equation, because when we combine orbital angular momentum vectors of two electrons, it would have various possibilities as predicted by quantum mechanics, which is written as we can write capital L is equal to L1 plus L2 to L1 minus L2, or L1 plus L2, L1 plus L2 minus 1, L1 plus L2 minus 2, etc. L1 minus L2. So they combine with third orbital angular momentum or orbital angular momentum of third electron, and so on. So the resultant orbital angular momenta L can have values like 0, 1, 2, etc. Then again similar procedure will be followed for spin vectors. That is, spin vectors of various electrons are to be added, S1 plus S2 to S1 minus S2, like that. And then capital L and capital S will be combined to give J. Then again you have to note, spin of an atom will be an integer if even number of electrons in the atomic system, and will be a half integer for odd number of electrons in the system. And therefore for calculation of J there is certain rules, that is J is equal to L plus S to L minus S, L plus S to mod L minus S in steps of 1. And for a given value of L, the allowed values of J are given by, there are two cases. One is L greater than S, then there will be 2S plus 1, which is small. That is 2S plus L greater than S means S is small. So 2S plus 1 values of J. And if L is less than S, then L is small. Then there will be 2L plus 1 values of J. So that is, there are many values of J. That shows degeneracy. So as an example, for an atom containing only one electron, that spin will be half. Spin of total spin will be the spin of one electron, that is half. For two electron system, S will be, there is 1 or 0 depending on whether spin vectors are parallel or anti-parallel. Correct? For a 3 electron system, S may be 3 by 2 or half. For a 4 electron system, it can be 2, 1, 0. So S is an integer. The total S is an integer or even multiple of half if even number of electrons are there in the system, and an odd multiple of half or odd number that provided if the number of electron is odd. Correct? So if S is an integer, J will also be an integer for even electron system. For odd electron system, S will be an odd multiple of half, and therefore J also will be an odd multiple of half. And a particular case or special case, if capital L is equal to 0, then there is no other value. J will be having only one value, that is the value of S itself. So this is an extension of this LS coupling, Russell-Saunders coupling. So here it is JJ coupling. JJ coupling is employed when the interaction between the spin and orbital vectors of each electron is stronger than interaction between either the spin vector or the orbital vector of the different electrons. The orbital and the spin angular momenta of each electron in the atom will be coupled or added to obtain the resultant angular momenta of the electron, total angular momentum of the electron, right? That is Ji is equal to Li plus Si, where we are getting the total angular momentum of each electron separately. So J1, J2, J3, etc. So that the net total angular momentum of the entire atom will be the sum of the total angular momentum vector of each electron, that is J1 plus J2 plus J3 in vectorial addition. So we will not go in detail this JJ coupling, as it is generally seen in heavy atoms. For our discussion in this undergraduate studies, we are focusing on one electron system or two electron system, not heavy atoms. Okay, so we will be mainly in focusing on LS coupling. Here we discuss atomic or optical spectra. There are two classes. The outer or valence electron of an atom determine the chemical and optical properties of the atomic system. There is a movement of valence electron between shells or states decide the kind of spectra or energy of the emission. For example, the electrons in the closed shell or that inner orbits, that will not take part in the spectral emission. Spectral emission is due to this exchange of energy or this release of energy due to the shifting of electron from one electronic state to another state. Okay, so inner electrons will not take part in this process. So depending on the number of these valence electrons in the outer shell of an atom, the atoms or atomic spectra are generally divided into two classes. One is one electron atoms and the corresponding one electron spectra, and the other is many electron systems. So in alkali metals like lithium, sodium, potassium, etc., they have only one valence electron outside the completely filled subshell. And this single electron in the valence shell of the alkali metals behave more or less like orbiting electron in hydrogen atom, and hence we say that alkali metals produce hydrogen-like spectra. So this kind of spectra emitted by alkali metals due to the transition of single electron in the outermost shell are known as one electron spectra. So in many electron systems, atoms will have more than one electron in the outermost shell, which are responsible for optical spectra. So outermost electrons may be called optical electron. That is a general terminology. Okay. So other electrons inside the completely filled subshells will not have roles in optical spectra. And these optical electrons that will fix the kind of spectra emitted by that atomic system. So atoms have got equal number. Atoms, for example, these all alkali metals, they will have identical one electron. Alkaline earth metals, they all have identical two electrons in the outermost shell. So that valence electron number, that gives a kind of spectra, and we say that there is an identical spectra. So accordingly, we say that one electron spectra or many electron spectra. So alkaline earth metals belongs to the category of two electron system and emit similar kind of spectra. Okay. Okay, so here we will elaborate our discussion on LS coupling to understand the spectral emission in light elements. So we had discussed in the last session that energy of a particular state does not depend on L or ML, but it depends on the value of total angular momentum quantum number J. So if there is only one value of J, there will be only one energy state. If there are more J values, there will be more energy states. Okay, so for a particular shell or a particular subshell, say S, P, D, F, etc., there will be fixed value of N and L, but there will be different values of J, which we have already seen. There is J is equal to L plus S minus 1, etc. to L minus S. That is, for a given value of L, the allowed values of J are given by two cases. One, for L greater than S, there will be 2S plus 1 values of J, and the other L less than S, there will be 2L plus 1 values of J. That is, there are certain values of J. So for each value of J, there is a particular energy level. So allowed values of J brings in multiplicity of the state and difference in energy during transitions. So the state of this atomic system we can represent in terms of S, P, D, F, etc. depending on the value of L. For L is equal to 0, it is S. L is equal to 1, it is P state. And for this S state, when L is equal to 0, the spin is half. So out of L and S, L is 0, L is smaller than S. Then multiplicity will be 2L plus 1, and there will be only 1. That is, there is only one value of J, and it is nothing but S itself, because L is 0, L plus S is S itself. So J is also half. So no multiplicity and only one state for L is equal to 0 state. And there is a spectroscopic notation, general pattern. That is, the state of an atom is represented as principal quantum number times superscript multiplicity and subscript J value to the state corresponding to the L value. So for S state, you can write, if N is 1, you can write it 1, 1 is half. N is 2, you can write 2, 1 is half. Because that superscript 1 indicates that there is only one state. There is no multiplicity, is only 1, no multiplicity. Okay, but in the case of P, D, F, etc., there will be multiplicity 2 that we will see in the next slide. Here in this slide also 2 electron system is also shown. That is, for a 2 electron system, 2 electrons are having S1 plus half and S2 minus half. Okay, in that case, if these two cases, 2 electrons will have spin half. So when 2 electrons are aligned parallel, then we say that S1 plus S2 will be, resultant S will be plus 1. Then we say that it is triplet state. Whereas if S1 and S2 are anti-parallel, one is plus half and the other is minus half, then the resultant spin will be 0. So if resultant spin is 0, then multiplicity will be 2 into 0 plus 1, that is equal to 1, and we call it singlet state. And if the resultant spin is 1, then 2 into 1 plus 1 is 3, that is called a triplet state. So this will be seen in 2 electron system, maybe like helium or something. But we are not going into that discussion here. Today in our discussion we focus on 1 electron system. So we will elaborate 1 electron system in the following slides as well. So here it is, spectral terms and term symbols. Okay. So atom can be represented by capital letter S, P, D, F, etc. corresponding to the effective orbital angular momenta of outermost electrons. So we are talking in terms of LS coupling scheme. So what we have just seen is, our previous slide what we have discussed was S state. For S state, L is equal to 0 and there is no multiplicity, there is only one value. Or J is having only one value and hence no multiplicity, and there is only one energy state. Because energy state is decided by J value, not L or ML. For a single electron atomic system which is in P, D or F like that, such states, then the multiplicity is given by 2s plus 1, because L is more than S, therefore it is 2s plus 1. Then 2 into half plus 1, that is equal to 2. So there will be 2 J values, L plus S and L minus S, and hence 2 different energy states would be possible. So these 2 states in the case will be expressed as superscript multiplicity and subscript, that is J, to the state corresponding to L value, which is given that green square, that is 2s plus 1 is given as superscript. L, whatever is L value, that, for example, L is equal to 0, it will be S. L is equal to 1, it will be P, something like that. Then the J value will be given as subscript. As an example, for L is equal to 1, it is P state and hence 2 energy state. So you can write it as superscript 2 P half and 2 P 3 by 2. If L is equal to 2, then it is D state, then you can write it as 2D 5 by 2 and 2D 3 by 2. So this is how spectroscopic notations will be presented, and this describes spectral terms or energy states associated with atomic state system in vector atom model, and this helps us to explain various spectral lines, additional spectral lines. Okay, now we will see selection rules. So there are certain restrictions on the transition of electrons from one energy level to another energy level, and it is based on quantum mechanical results coming from solutions of Schrodinger equation and are known as selection rules. These selection rules govern the transition actually, and with the help of these selection rules we will be able to explain many atomic spectra. So in vector atom model there are 3 basic selection rules, one each for L, S and J. They are change in resultant orbital angular momentum L, that is delta L is equal to plus or minus 1. That is, only those spectral lines are observed for which state of the atomic system described by the value of L is allowed to change only by plus or minus 1. That is, L can change from 0 to 1 or from 1 to 0. But 0 to 2, 2 to 0, etc. will not be allowed. For such spectral lines cannot be expected or cannot be observed. That is, transition is possible between S and P levels, because that is delta L is plus or minus 1. Or P to S, but S to D, D to S, P to F, those type of transitions are not allowed. Then second one is that no change in the value of spin angular momentum, S is allowed during transition, that is delta S is 0. Okay, then third one is for J, that is delta J is equal to plus 1 or plus or minus 1 or 0. That is, the restriction is one additional restriction is given, that is 0 to 0 is excluded. That is change in J due to 0, that is J is equal to 0 is allowed, but not due to transition from J is equal to 0 to J is equal to 0 state. Okay, so example 2D 3 by 2 to 2P 3 by 2 is allowed. Even though delta J is equal to 0, it is not from J is equal to 0 to J is equal to 0. It is from J is equal to 3 by 2 to J is equal to 3 by 2, right? So these are some basic selection rules which are to be strictly followed. And that with the help of this, because this comes from quantum mechanical theories, sound basis there for this selection rule, and so these selection rules are to be perfectly followed while describing or explaining these atomic spectra. Okay. So next is strength of transition or intensity rules. So this strength of the transition is decided by a set of rules. That is what we call it intensity rules. And these intensity rules are given in a nutshell on the slide. That is, first one is delta J is equal to delta L, or delta L is equal to delta J. Then transition is expected to be the strongest. That is transition from which for which L and J change in the same manner are comparatively stronger than those for which they are not changing in the same manner. That is, if delta L is not equal to delta J, transition will be weak, right? Another rule is the transition for which L and J increase, that is L to L plus 1, J to J plus 1, they are less intense than those for which L and J decrease, that is L to L minus 1, J to J minus 1, etc. And the last one is the transition for which change in L and J are equal but opposite, that is delta L is equal to minus delta J, which are not possible, or which is they are forbidden transitions. So this combined combination of these selection rule and intensity rule, which is shown in on the slide in that yellow square, you can see delta L is equal to minus 1, delta J is equal to minus 1, that is the strongest. Because that one condition is delta L is delta J satisfied, one is it is going to lower value, right? Then delta L is minus 1, delta J is equal to 0, it is less intense. Then delta L is equal to plus 1, delta J is equal to plus 1 weak. You just analyze, compare, connect that intensity rules and the selection rule, then you will understand how it comes out. Okay, so this specify these various transitions and their behavior, whether it is strong, strongest, weak or weakest, something like that, whether it is forbidden. So you just analyze this particular yellow box. Okay, so now we will try to analyze, or we will extend this vector atom model to explain H alpha line, that is H alpha line of Bohr, that Balmer series. Okay, so in Bohr atom model we had discussed this line spectra. Balmer series comes in the visible range due to transition from n is equal to 3, 4, etc. to n is equal to 2 level. The first line of Balmer series is H alpha line due to transition from n is equal to 3 to n is equal to 2. And the H beta is due to transition from n is equal to 4 to n is equal to 2. Then H gamma due to transition from n is equal to 5 to n is equal to, etc. So that is how we describe various lines in Balmer series. And when wavelength of these Balmer series lines are calculated, you can see that it comes within this visible spectrum. Visible spectrum means 350 or 380 nanometer to 7500, 8000 nanometer. Okay, that is the range. So here our discussion is on H alpha line. That is, as per Bohr atom model, H alpha is supposed to have just one energy or single line. That is, H alpha is a specific deep red visible spectral line in the Balmer series with a wavelength of 656.28 nanometer in air. That 656 is almost close to red, or almost red color. But high resolution studies established that this H alpha line is not a single line, but it consists of many, or that is, instead of single line, there may be, sometimes there was a discussion, there was a explanation that it is a doublet spectrum. Then later, now we say that it is having 5 components or 7 components, like that. So this could not be explained with Bohr atom model. So this is what we call fine structure. So in atomic physics, this fine structure describes the splitting of the spectral lines of atoms due to electron spin and relativistic corrections to the non-relativistic Schrodinger equation. And it was first described or measured by precisely by two scientists, this H alpha spectrum, was analyzed first by two scientists, A. Michelson and Edward W. So now we will try to account for these fine structure of H-alpha lines using this vector atom model. So hydrogen atom belongs to one electron system, and therefore that capital L, which represents the atom, is nothing but it is equal to the orbital angular momentum of single electron, that is small l. Similarly, capital S is equal to small s and capital J is equal to small j, because only one electron. So electrons, that notation and atoms notation should match, right? So for upper state, when n is equal to 3, because Bohr atom model, it is from this H-alpha line is due to transition from n is equal to 3 to n is equal to 2. So principal quantum number n is equal to 3, then orbital angular momentum quantum number of electron L can have value from 0 to n minus 1. We have seen earlier, that is 0, 1, 2, right? So, and here we say that since there is only one electron, that state of the atom capital L and the state of the electron small l are matching, same. Therefore, capital L is equal to small l, and small l is having values 0, 1 and 2. Therefore, capital L is having values 0, 1 and 2, because there is only one electron and spin is equal to half. Now for this n is equal to 3, we have to identify what are the possible energy states. That is, for L is equal to 0, L is equal to 1 and L is equal to 2, what are the possible energy states? Okay, because there n is equal to 3 and associated we have got S, P and D states. First we will take L is equal to 0 state, that is S state. For S state, L less than S, and there is only one spectral term, that is 12 plus 1 is equal to 1. Therefore it is S half, 1 S half. Then for L is equal to 1, multiplicity is 2S plus 1. Right? That is 2S plus 1 will be equal to 2. 2 into half plus 1 is equal to 2. So there will be two spectral terms which are 2p 3 by 2 and 2p half. And for L is equal to 2, there are again two spectral terms which are 2d 5 by 2 and 2d 3 by 2. Right? So the spectral terms or possible spectral levels or energy states for n is equal to 3 are as per vector atom model. One is 2d 5 by 2, then 2d 3 by 2, then 2p 3 by 2, then 2p half and 1s half or s half. Right? So there are 5 energy states. Similarly, you can work out for n is equal to 2, and the possible states would be 2p 3 by 2, then 2p half and s half or 1s half. Right? So there are 5 levels in the top and one level or 3 levels, 3 energy states in the n is equal to that is 2 state. Okay, so with the help of these 5 top and 3 bottom, you can describe these various components of H-alpha line, H-alpha spectrum. Okay, we will continue with this fine structure of H-alpha line, and theoretically, if you analyze, if there are 5 energy states in the n is equal to 3 level and 3 energy states in n is equal to 2 level, then theoretically 15 transitions are possible. But you have to apply selection rules, that is delta L is plus or minus 1 and delta J is plus or minus 1 or 0. And this restrict or reduce the number of permitted transition to 7. So there are 7 transitions which are shown, that is 2d 5 by 2 to 2p 3 by 2, 2d 3 by 2 to 2p 3 by 2, like that. 7 various transitions are shown on the slide, and one figure is shown, that is Balmer spectrum, but that is not based on vector atom model, it is based on Bohr atom model, and there is only single line. But vector as high resolution spectroscopy tells that H-alpha line is not a single line, it consists of 5 components or 7 components, like that. So these, using these 7 transitions or like that, we may be able to explain, or we will be able to explain the possible component lines in the observed in H-alpha line, H-alpha spectrum. So a few of them are coincident levels. Out of these various 7 transitions shown, some of them are coincident levels and will give identical transitions and cannot be distinguished. So coincident levels are those levels where L values differ by unity, but J values are the same. Also, we can apply intensity rules. That is, some of these lines will be very intense, some of them will not be, or will be very weak. So taking into consideration all these coincident levels and these intensity rules, we can show that there are 5 reasonably good account, or 5 prominent lines. 5 prominent lines can be distinguished in H alpha, or we can say that there are 5 component lines. But there are publications which say that state that there are 7 component lines. Anyway, it is not a single line. Okay, H alpha line is not a single line, and hence cannot be explained with Bohr atom model. Many research papers are available on this, and I have also attached one old paper for you to read and familiarize. Okay, you may just search for some research paper on H alpha line and related studies. So it will be a good work. Wherever possible, try to read research papers. That will give you some scientific new thoughts and insight that will inspire you to do further research in your career as well. Okay, so I stop here. Thank you. Have a good time.